Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the IES or ESE, EMT, previous year prelims question in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes from mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why do you waste more time? So let's get started. So now we are going to solve the 31st question. See the question here. The following point charges are located in air, which is plus 0.008 microcoulomb at 0,0 meter and plus 0.05 microcoulomb at 3,0 meter and minus 0.009 microcoulomb at 0,4 meter. So now we have to find what is the total electric flux over a sphere of 5 meter radius with center 0,0. So basically in this question they are trying to say that there are three charges they are going to present at these particular points. So now we have to find how much amount of electric flux is passing through you can say how much amount of electric flux is passing through a sphere of radius 5 meter which is centered at origin. We need to figure out. So out of these four options, option B is the correct solution of this question. So let's solve this numerical. So basically there are three charges, Q1, Q2 and Q3. So the Q1 is equal to plus 0.08 microcoulomb and Q2 is equal to plus 0.05 microcoulomb and Q3 is equal to minus 0.09 microcoulomb. So these charges are going to present at 3 points which are also given in the question, which is Q1 is present at the origin, which is 0,0,0, and Q2 is going to present at the 3,0,0, and similarly Q3 is going to present at 0,4,0. So now there is a sphere of radius 5 meter. So now we have to find how much amount of flux is passing through this closed sphere. We need to figure out. As if you see clearly, this closed surface is going to enclose all the three charges within itself. So therefore, by using the Gauss law, we can know the total flux passing through any closed surface is equal to the charge enclosed by that closed surface. As you can clearly see that this Gaussian surface is going to, or you can say this closed surface is going to enclose all the three charges. So therefore now we have to find what is the addition of all this net charge present in this sphere. We need to figure out. So therefore which is Q1 plus Q2 plus Q3. So therefore you have to add all this Q1 plus Q2 plus Q3. So if we add all these three quantities, finally we are going to get the amount of flux passing through this closed surface is equal to 0.049 microcoulomb is the correct solution of this question. So now we are going to solve the 32nd question. See the question here. The vector statement of the Gauss law is. So now we have to find what is the vector statement of the Gauss law. So out of these four options, option D is the correct solution of this question. So let's solve this numerical. So now Gauss law, see in this question they are asking about what is the vector statement of the Gauss law. So basically what is the meaning of a Gauss law? So Gauss law is going to find you how much amount of electric flux which is passing through any closed surface. This is what we are going to figure out with the help of the Gauss law. So Gauss law states that the total electric flux through any closed surface is equal to the total charge enclosed by the closed surface. Means the Gauss law is going to basically tell you how much amount of total electric flux which is passing through any closed surface, which is going to figure out with the help of the Gauss law, which is equal to the total amount of charge enclosed by the closed surface. So therefore the total electric flux passing through any closed surface is equal to the charge enclosed by the closed surface. So flux we can write which is the surface integral of closed surface integral of d by ds bar is equal to charge enclosed we can write which is volume integral of the rho v into dv. So this statement we are going to call it as the integral form of the Gauss law, or we can even call it as the vector form of the Gauss law. Suppose if you want to write in another form, which is closed surface integral of d by ds bar is equal to volume integral of divergence of d bar into dv, because only a closed surface can enclose a volume. So because of that reason we can say this is called as the Gauss divergence theorem. So if you can see clearly, this both the equations LHS are equal, so therefore RHS also should be equal. So therefore we can say del dot d bar is equal to rho v. So therefore divergence of electric flux density is equal to volume charge density. So divergence of electric flux density is equal to volume charge density. This we are going to call it as the differential form of the Gauss law. But in the question they asked what is the vector form of the Gauss law, or we can even say which is the integral form of the Gauss law. So therefore this is the correct solution of this question. So basically the Gauss law is going to tell you the total amount of electric flux passing through any closed surface is equal to the amount of charge enclosed by that closed surface. So now we are going to solve the 33rd question. See the question here. A quantitative relation between the induced EMF and the rate of change of flux linkage is known as. So basically, which law is going to give you a relation between the amount of induced EMF with respect to the rate of change of flux? So out of these four options, option D is the correct solution of this question, which is the Faraday's law. So now we are going to solve this numerical. So now the Faraday's laws of electromagnetic induction is going to tell you that is the amount of EMF induced in any coil, it is called directly proportional to rate of change of flux. If the flux is constant with respect to time, it indicates that the amount of induced EMF is zero. That is the reason always it is proportional to the derivative of the rate of change of flux. So there is always a negative sign. So this negative sign is going to indicate that the amount of EMF induced, or we can say it is going to produce the current in such a way it is going to oppose the flux, or we can say it is going to oppose the Gauss. That is the meaning of this negative sign. This negative sign was given by the Lenz's law. So therefore we can say it is a combination of even Lenz's law. So if you want to know only what is the magnitude of the EMF, so you have to go for the magnitude, means you have to take only the positive value, which is plus and d phi by dt. So therefore the EMF induced, the magnitude value is directly proportional to rate of change of flux. So therefore we can say this is what which is given by the Faraday's law. So therefore it is going to relate the amount of induced EMF with respect to rate of change of flux in any coil. So this was given by the Faraday's law. So now we are going to solve the 34th question. See the question here. If E is equal to 0 at all the points on a closed surface, the first one is the electric flux through the surface is 0, and the second one is the total charge enclosed by the surface is 0, and the third one is the charge resides on the surface. Suppose if the electric flux is equal to 0 on the surface, then what we are going to see? Suppose if E is equal to 0 at all the points on a closed surface, so from this condition what are the things are going to true? Out of this 1, 2 and 3. So out of these four options, option A is the correct solution of this question, means only 1, 2 are only going to satisfy, but not the third one. So now I will solve this numerical. Suppose there is a closed Gaussian surface. At each and every point on this closed surface, if the electric field is 0, then what we are going to conclude from this is equal to 0, we need to figure out. As I have already told you, the total electric flux passing through any closed surface is equal to the amount of charge enclosed by the closed surface, which is phi is equal to total charge enclosed. So total flux is equal to closed surface in the left, d bar or ds bar is equal to charge enclosed. So d bar we can write, which is in the epsilon into E bar. So therefore epsilon into closed surface in the left, E bar or ds bar is equal to charged enclosed. See in the question they are given at each and every point on this closed surface, at this closed surface terminal, each and every point the electric field is 0. So therefore we can say if electric field is 0 at each and every point, definitely their closed integration is also equal to 0. So 0 into anything is again 0. So therefore the total charge enclosed by the closed surface must be equal to 0, and also it indicates that if this is equal to 0, then definitely the total flux passing through the closed surface is equal to 0. If electric field at each and every point on that Gaussian surface, if it is 0, then definitely the total charge enclosed by the closed surface is equal to 0, and also the amount of electric flux passing to the closed surface is equal to 0. Only these two things we can figure out. So therefore option 1, which is the electric flux passing to the closed surface is 0. So first one is correct, and the option 2, the total charge enclosed by the surface is 0. But the third one is the charge resides on the surface. That we don't know, because we are not going to conclude from these things. Only two things we can conclude, which is the total flux passing to the closed surface is equal to 0, and also the amount of charge enclosed by the closed surface should be equal to 0. Only these two things we can conclude, but not whether the charge is going to reside or not. That is not we are going to conclude. So therefore suppose if there is a plus q and a minus q, so this is called as a dipole. So therefore always for a positive charge the electric field is going to radiate outward, whereas for the negative charge the electric field is going to radiate inward towards the charge. So positive charge is going to radiate the electric field in this manner, whereas the negative charge is going to take the electric field inside, and from positive to negative charge the electric field is going to move in this manner. So this is called as the electric lines of force or the electric field diagram of a dipole. Suppose if you are going to take any Gaussian surface, if you are going to take any closed Gaussian surface, you can see clearly the number of electric field lines which are going outward is equal to number of electric field lines coming in inward the Gaussian surface. So you can see clearly here two lines are going outward and two lines are coming inward. So therefore we can say net outward is equal to net inward. So therefore net amount of flow in this closed surface is equal to 0, because it indicates that the charge enclosed by this Gaussian surface is equal to 0. So therefore we can say clearly if any net flow which is going to present in a Gaussian surface, then only we can say the flux is not equal to 0, otherwise the net flux is equal to 0. So therefore we can say here only if E is equal to 0, only two things we are going to conclude, which is the charge enclosed is equal to 0 and also the flux through the closed surface is equal to 0. Only these two things we can infer from this E is equal to 0. So now we are going to solve the 30th question. See the question here. The electrostatic force of repulsion between the two alpha particles of charges 4 into 10 to the power of minus 19 coulomb each and separated by a distance of 10 to the power of minus 10 centimeter. In the question they also given epsilon naught value is equal to 8.85 into 10 to the power of minus 12. So based on this data we have to find what is the amount of repulsion force between the two alpha particles of same charge. They are going to separate by distance of 10 to the power of minus 10 centimeter. So out of these four options, option C, which is 14.4 into 10 to the power of minus 4 Newton, is the correct solution of this question. So let's solve this numerical. So in this question they are given two charges Q1 and Q2. They are going to separate by distance of R. So these charges are called as the alpha particles of same charges. So if you are going to keep any two same charges or like charges, the force will be repulsion. Suppose for unlike charges they are going to get attract and like charges are going to get repel. So here Q1 is equal to Q2, which is 4 into 10 to the power of minus 19 coulomb, and the distance between the charges is 10 to the power of minus 10 centimeter. So if you want to convert in terms of meter, we are going to get 10 to the power of minus 12 meter. So based on this data we have to find how much is the amount of repulsion we need to figure out. So this is called as a Coulomb's law. Coulomb's law is going to give you the amount of force between the two charges, which is F is equal to Q1 Q2 by 4 pi epsilon R square, where epsilon is called as the permittivity of the medium, which is epsilon naught into epsilon R. So epsilon is called as the permittivity of a free space, whereas epsilon R is called as the relative permittivity of a medium with respect to the free space or the vacuum. So whenever the epsilon value is higher, it indicates that force is lesser. It means the permittivity of a medium is trying to oppose the electric field in a given region. So therefore the epsilon value, which is 8.85 into 10 to the power of minus 12. And also I have told you in the question they have not given anything regarding the epsilon R. So if they are not given anything regarding epsilon R, it indicates that epsilon R value is equal to 1. So therefore we can say 1 by 4 pi epsilon value, which will be equal to 9 into 10 to the power of 9. So therefore this value now will become, which is epsilon naught, because epsilon R is equal to 1. So therefore you can substitute all these values in this equation. So Q1 Q2, which is 4 into 10 to the power of minus 19 whole square, into 1 by 4 pi epsilon naught, which is 9 into 10 to the power of 9, and R value, which is 10 to the power of minus 12 whole square. So if you do the simplification of this data, finally we are going to get F is equal to 14.4 into 10 to the power of minus 4 Newton. So this is the correct solution of this question. So now we are going to solve the 36th question. See the question here. The electric field lines and the EQ potential lines are. So basically in this question they are asking about the electric field lines and the EQ potential lines are, how they are going to get intersect. So out of these four options, option C, they are going to cut orthogonal is the correct solution of this question. So let's solve this numerical. So now here the voltage difference between any 2 points, which is VAB is equal to VB minus VA is equal to work done per unit charge is equal to negative of the integral of A to B into E bar dot EL bar. This is the basic expression. So now in the question they are asking what is the intersection of the electric field and the equipotential planes. So basically equipotential plane means on that plane the voltage at each and every point is same. So therefore we can say, suppose if you take a equipotential, then any 2 points on that surface voltages will be equal. So if you keep here, VB minus VA is nothing but 0 because both are equal. So 0 is equal to minus integral of A to B E bar dl bar. So clearly, if this has to be equal, indicates that this dot product should be equal to 0. So whenever this dot product is equal to 0, as we can already say that theta is the angle between the E bar and dl bar. So therefore now, if you know dot product which is E into dl into cos theta is equal to 0, if this has to be equal to 0, indicates that these are non-zero values. So definitely this has to be 0, then only non-zero value into 0 value is equal to 0. So cos theta is equal to 0, it indicates that theta is equal to 90 degrees. So theta is the angle between the electric field and the dl bar. So therefore we can say, if this is the E bar, then definitely we have to move in a perpendicular to the electric field in such a way they are going to cover the 2 points A and B. So therefore the potential at VA is equal to potential at point B. So therefore we can conclude that this is the equipotential plane which is perpendicular to the electric field. So therefore at each and every point on that equipotential plane, or we can say that voltage is equal to same. So therefore now, suppose for a point charge we are going to get spherical spheres which are the equipotential surfaces, whereas for a sheet charge we are going to get a equipotential surfaces which are the planes which are the parallel to the sheet charges, whereas for a line charges we are going to get a cylinder shape, or we can say concentric cylinders are the equipotential surfaces for a line charge. So all these things we have discussed in our course also. So therefore we can say clearly the electric field and the equipotential surfaces are going to get orthogonal to each other, or they are going to cut orthogonal to each other. So now we are going to solve 37th question. See the question here. According to Gauss law, the surface integral of the normal component of the electric flux density D over a closed surface containing the charge Q is equal to. So in this question they are saying that what is the surface integral of the normal component of the electric flux density over that closed surface we need to figure out. So out of these four options, option C is the correct solution of this question. Q is the charge enclosed by that surface. So now let's solve this numerical. Now listen, see the Gauss law is going to tell you, suppose if you are going to take any Gaussian surface, so you have to take any closed surface. Any closed surface is called as the Gaussian surface. So the amount of electric flux passing through this Gaussian surface is equal to the amount of charge enclosed by this Gaussian surface or closed Gaussian surface. So therefore the amount of flux passing through this closed surface is equal to charge enclosed by that closed surface. So this is called as the closed surface integral of the d by ds bar is equal to charge enclosed. In the question they are given, this closed surface is going to enclose the charge which is equal to Q. So therefore now, suppose if you want to know what is the d bar is equal to, so d bar is equal to epsilon into E bar. So therefore you can take epsilon constant outside of the integration. So epsilon into closed surface integral of E by ds bar is equal to Q. So if I take this epsilon downward, we are going to get closed surface integral of E by ds bar is equal to Q by epsilon. But in the question they are asking about the closed surface integral of the normal component of the d by ds bar is equal to charged enclosed. So therefore this is the correct solution of this question. This is another way of writing in terms of the electric field, but this is the in terms of the electric flux density, which is the closed surface integral of the d by ds bar is equal to Q. So therefore this is the correct solution of this question. So now we are going to solve 38th question. See the question here. Consider the following statements associated with the basic electrostatic properties of ideal conductors. So these are the 5 properties they are given for the electrostatic properties of basic of ideal conductors. So out of these 5 we need to say which are the correct one. The first one is the resultant field inside is 0, and the second one is the net charge density in the interior is 0, and the third one any net charges reside on the surface, and the fourth one is the surface is always equipotential, and the fifth one is the field just outside is 0. So out of these 5 statements for electrostatic properties of ideal conductors, which are the true statements out of these 5 we need to figure out. So out of these 4 options, option A is the correct solution of this question, which is the 1, 2, 3, 4 are the only correct but not the 5th one. So now let us solve this numerical. Suppose there is a solid conductor. So for the solid conductor, suppose externally I am going to pass an electric field. So as this electric field is going to pass near the solid surface, it is going to enter this, or you can say it is going to enter this the solid surface orthogonally and it is going to leave this solid sphere orthogonally at 90 degrees. So therefore it is going to enter in this manner and it is going to leave in this manner. But the electric field inside is ideal current is equal to 0, because here suppose there is a solid surface, so therefore it is going to always become a neutral, means neutrally charged. So therefore the negative charge is going to reside on the surface and the positive charge is going to reside on the surface. So as a positive charge is going to radiate the electric field, so here there will be positive charge and here it will be a negative charge. So overall charge will become 0 because it is a neutral one. So therefore we can say the charges are going to reside on the surface, but inside charge is 0. So if you take any closed surface, any Gaussian surface which is enclosing inside this ideal conductor, as the charge enclosed itself is equal to 0, so therefore we can say the amount of flux passing through this closed surface is equal to charge enclosed. As a charge enclosed by this Gaussian surface inside this ideal conductor is equal to 0, so flux is equal to 0. As flux itself is equal to 0 means D is equal to 0. So D itself indicates is D is equal to 0 means E is equal to 0. So therefore we can say the electric field inside ideal conductor is always equal to 0 because the charge enclosed itself inside is equal to 0. So therefore only charge is going to stay or reside only on the surface but not at the inside, and electric field is going to enter orthogonally to the surface and it is going to leave orthogonally from the surface, and inside electric field is always equal to 0, but electric field can present outside the ideal conductor. So therefore, and also we can say, as I've already told you, VAB is equal to VB minus VA is equal to W by Q is equal to minus integral of A to B E bar dot dl bar. As I've already told you, the electric field inside is 0, so 0 into anything is again 0. So therefore VB minus VA is equal to 0. It indicates that VB is equal to VA. So therefore if you take any 2 points inside this ideal conductor, always the potential is equal. It indicates that there is a constant potential. So therefore we can simply say that the potential inside this ideal conductor is constant at each and every point inside this ideal conductor, or we can say it is a constant potential device. So therefore now we will discuss the basic electrostatic properties of ideal conductor. The resultant electric field inside is 0 because there is no charge enclosed by the Gaussian surface. So therefore the total flux passing through that closed surface is equal to 0. So therefore we can say the electric field inside that ideal conductor is always equal to 0. The net charge density in the interior is 0 because I have already told you the net charge enclosed inside is 0. So because of that the electric flux is 0 and the electric field is also 0. And if any net charge is going to reside on the surface, only on the surface of the closed surface, or we can say only at the surface of this ideal conductor the charge is going to present, but not at the inside of this conductor and also ideal conductor. And the surface is always equipotential. As I have already told you, as electric field inside is 0 means the potential at each and every point inside that, we can say on that conductor is always same, or we can say it's a equipotential surface. So therefore, and the field just outside is non-zero because see electric field outside that ideal conductor is non-zero, but inside it is 0. So therefore in the question they are given it is 0. So therefore fifth is the wrong option. But the electric field just outside is non-zero, but inside it is 0, but not at the outside. So therefore we can say only 4 statements are the correct, but not the 5th statement. So now we are going to solve the 9th question. See the question here. In practice, the earth is chosen as a place of 0 electric potential because it. So in practice, why earth is chosen as a 0 electric potential? What is the reason? So out of these 4 options, option D, it has almost constant potential is the correct solution of this question. So let's solve this numerical. So now earth will be basically an ellipse in shape, but we are going to assume it is nearly a spherical one. So because of that reason it is going to have a radius r, and also the charge of the earth we are going to assume as q, and r is the radius of the earth. So because of that reason we can say the potential of the earth, which is expression V is equal to q by 4 pi epsilon r, as the q is very small of earth, whereas the radius of the earth is very high. So therefore we can say as the denominator is very high when compared to numerator, so overall ratio will become nearly equal to 0. So therefore in practice we are going to assume the or we can say in practice the earth potential we are going to assume it as 0 because at each and every point the potential is constant. So therefore at each and every point on that surface the electric potential of the earth is constant and it is nearly equal to 0. So this is the reason we are going to assume it is nearly equal to 0, but not exactly. So therefore because at each and every point on the surface of the earth the potential is constant, so because of that reason we are going to assume it is nearly equal to 0. So this is the correct solution of this question. So now we are going to solve the last question of this lecture. See the question here. The capacitance of a conducting sphere of radius r with a total charge of q uniformly distributed on its surface is. So basically in this question they are given a sphere. It is going to have some charge of q and also the radius of the sphere is r. So now we have to find what is the relation between the capacitance of the sphere and also based on the charge. So out of these four options the capacitance is independent of the charge. So now let us solve this numerical. So option D is the correct solution of this question. Suppose there is a sphere of radius r. So now here they are going, it is a conducting sphere, it is going to have some charge q and also the radius of the sphere is r. So based on this we have to find what is the capacitance of this sphere we need to figure out. See, as this is a sphere it is going to have some voltage, so voltage is equal to q by 4 pi epsilon r. So but what is the capacitance? Capacitance is equal to ratio of the charge by voltage. So q by v, if you do this one we are going to get 4 pi epsilon r. So therefore we can say the capacitance of this sphere is equal to 4 pi epsilon r. So capacitance is going to depend only on the permittivity of the medium and also on the radius of the sphere, but it is independent of the charge of a sphere. So it is going to independent of the amount of charge present on that sphere. It is going to depend only on the permittivity of the medium and also r is the radius of the sphere. So therefore we can say clearly C is independent of q. So therefore C is independent of q. So this is the correct solution of this question. The capacitance of any sphere it is going to depend only on the permittivity of the medium and also on the radius of the sphere, but it is independent of the charge which is going to present on that sphere. So this is the correct solution of this question. So by this lecture we have successfully completed the 40 questions which are the previous year questions of the ESE of EMT in a very detailed manner. And if you like the content of our channel then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever you upload a new video the direct notification comes to mobile. If any improvements needed in our lectures then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.